Welcome back to the Deep Dive. Today we are rolling up our sleeves and doing some heavy lifting. We're tackling a topic that I think makes even seasoned tech people sweat a little bit.
It definitely has that reputation, yeah.
We're talking about the cloud. And, usually when we say that, we picture this fluffy, abstract thing where data just sort of floats around.
In the ether.
Exactly. But when you actually dig into the source material we have, these detailed notes on AWS network services, you realize pretty quickly the cloud isn't fluffy at all.
No, not at all.
It's rigid, it's structured, and honestly, it looks a lot like plumbing.
That is the perfect way to describe it. It is digital plumbing. We are looking at the pipes, the valves, the gates, and the walls that make everything work.
And if you don't get that plumbing right, the house floods.
It absolutely does.
And looking at this file, AWS Practitioner 304, it is just alphabet soup.
Yeah.
VPC, CIDR, NACL, ENI, IGW. Feels like you need a decoder ring just to get started. So here is our mission today. We are going to decode this. We are going to strip away the jargon and figure out how you actually build a network that is secure, but also, useful.
That's the core tension, isn't it? It's a balancing act between being a fortress and being a hub. And it all starts with one fundamental concept.
The land itself.
The virtual private cloud, the VPC.
Right. So in the notes, the VPC is described as your own isolated section of the AWS cloud. But what struck me is that default state. Because when I think cloud, I think connected.
Instantly connected, yeah.
But when you create a new VPC, what is it connected to?
Nothing. Absolutely nothing.
It's just a void.
Think of it as buying a plot of land in the middle of nowhere. You have the deed, it's yours. But there are no roads leading to it.
No power lines, no phone lines.
None of that. So if you spin up a server inside that brand new VPC, it is completely on an island. It cannot talk to the internet, and the internet definitely can't talk to it.
So that's the ultimate security by isolation.
Correct. It's a closed loop. The whole game of AWS networking is deciding very deliberately where to build the bridges and where to build the walls. You start with walls, and you carve the doors out yourself.
Okay, so let's start building. We have our land. Now we need to subdivide it. The source material talks a lot about subnets.
Right. The rooms inside the house.
Exactly. And not all rooms are the same. You wouldn't put your front door in your bedroom.
You would hope not. So the notes outline three distinct flavors of subnets. First, you have the private subnet. This is that default state we just talked about.
Okay, no route to the internet.
None. This is where you'd put a database, right? Something you want to keep hidden.
The family jewels.
Exactly. Then you have the public subnet. Now, here's a nuance that trips people up all the time. A subnet isn't public just because you call it that.
You can't just stick a label on the door.
No. The notes are very specific. To make a subnet public, you have to attach a specific piece of virtual hardware called an Internet Gateway, or IGW.
Okay, the IGW.
And then you have to update the routing tables to say, hey, for internet traffic, go through this door.
So the IGW is the actual front door, and the route table is the sign pointing to it.
Precisely. If you don't have both, you just have a private room with a confusing sign on it.
Got it. And then there was a third type, the VPN-only subnet.
This is for the corporate crowd. Say you're a bank, you want to use the cloud, but you don't want your data just traversing the open internet, so you set up a virtual private gateway, a VPG.
Another gateway, IGW for internet, VPG for VPN.
You got it. The VPG creates a secure, encrypted tunnel back to your corporate office. It's like building a private underground tunnel from your house directly to your office. You never have to go outside.
I like that image. Okay, so we have our rooms. Now we have to talk about addresses, and this is where my eyes usually glaze over. CIDR blocks.
Ah, the dreaded CIDR math.
Classless interdomain routing. Even the name sounds unfriendly. And then you see these numbers like 172.31.01016. What does that /16 actually mean?
It's simpler than it looks, I promise. Think of an IP address like a street address. Part of it is the street name, part is the house number. The slash number, the 16, tells you where that line is drawn.
Okay, so for 16.
It means the first two numbers, the 172.31 part, that's your street name, that's locked. Every device in your VPC will start with 172.31.
And the rest of the numbers are for me to use.
That's your free space. That's where you can assign all your house numbers to your servers and databases.
So is a 16 a big network or a small one?
It is huge. And this is the counterintuitive part. The smaller the number after the slash, the bigger the network.
Wait, really? Smaller is bigger. That feels backward.
Think of it like a pie. The slash number is how many times you've sliced it to define the network part. Fewer slices mean you have this massive chunk left over for addresses. A 16 gives you over 65,000 IPs.
Wow, okay, that's plenty.
But then you carve that up into subnets, which are usually 20. Now, since 20 is a higher number, you've sliced the pie further.
So you have less room for hosts.
Exactly. A 20 gives you about 4,000 IPs. Still a lot, but you have to plan that space carefully.
Speaking of planning, I found a scenario in the notes that I think is really common. Let's say I have a database in a private subnet. It's locked down.
Right.
But it needs to download a security patch. It needs to reach out to the internet, but I can't let the internet reach in. It feels like a catch-22.
It is. You want to make a phone call, but you don't want to receive any cold calls.
Exactly. How do we solve that?
For IPv4, the solution is something called a NAT gateway, network address translation.
Okay, how does that work?
You put the NAT gateway in your public subnet. Your private server sends its request to the NAT gateway. The gateway then goes out to the internet for you, gets the patch, and passes it back.
So it's like a courier.
A bodyguard that does your shopping. The internet only ever sees the NAT gateway's public IP. It has no idea your private server even exists.
That makes sense. But the notes had a specific call-out here for IPv6. It said IPv6 doesn't use NAT.
This is a key technical detail. There are so many IPv6 addresses we don't need to translate them to save space, which is why NAT was invented.
So if you don't use NAT, how do you get that outbound-only security?
You use an egress-only internet gateway.
Egress only. I love how literal that is.
It does exactly what it says on the tin. Traffic can exit egress, but it cannot enter. It enforces that no cold calls rule at the gateway itself.
Very cool. Okay, while we're on addresses, I have to bring up the gotcha I found in the notes about elastic IPs. This actually made me laugh.
Ah, the billing quirk.
So an elastic IP is a static public IP.
Yeah.
And usually in the cloud, the rule is pay for what you use.
Generally, yes.
But the notes explicitly say, if you reserve an elastic IP and you don't use it, AWS charges you. But if you do use it, it's free.
It does seem completely backward, doesn't it?
It's like getting a parking ticket for having an empty driveway.
It is. But you have to look at it from their perspective. Public IPv4 addresses are a scarce global resource. We've literally run out of them.
So if I claim one and just let it sit there,
you are hoarding a resource that someone else could be using. So AWS charges you a penalty for, well, loitering.
I'm paying for loitering. I love it.
Yeah.
Okay, so we've got our VPC, our subnets, our addresses, now security. We have security groups and NACLs, and I'll admit, I always get these mixed up.
You and everyone else. It's the single most common point of confusion.
They both just seem to allow or deny traffic. Why do we need both?
Okay, they work very differently. Let's start with security groups. The notes say they act at the instance level. So this is the firewall right on your server.
On the machine itself.
Exactly. But the magic word for security groups is stateful.
Stateful. What does that mean in plain English?
It means it has a memory. It tracks the state of the connection. Think of it like a really observant bouncer at a club.
Okay, I'm at the club.
You go to the door, the bouncer checks your ID, sees you're on the list, and lets you inside.
Great.
Now, later on, you want to leave. Does the bouncer stop you and check your ID again to let you out?
No, of course not. He just saw me go in. He knows I'm good.
Exactly, he remembers. If traffic is allowed in, the return traffic is automatically allowed out. You don't need a separate rule.
Okay, that's the smart bouncer.
Yeah.
What about NACLs? Network Access Control Lists.
NACLs act at the subnet level. They're the perimeter guard for the whole neighborhood, not the house. And they are stateless.
So, no memory.
None. Total amnesia. If you pass the guard to get into the subnet, that's fine. But when you try to leave, the guard at the exit looks at you like he's never seen you before.
Who are you? Where are you going?
Exactly. So with an NACL, you need an allow rule for traffic coming in, and D, a completely separate allow rule for the traffic going back out.
And if I forget that outbound rule?
Your server gets the request, it processes it, it tries to send the answer back, and the NACL just slams the door in its face. Black hole.
That sounds like a nightmare to debug.
It is notoriously difficult. That's why security groups are your daily driver. They're easy. NACLs are more of a blunt instrument for blocking things at the border.
Bouncer versus the amnesiac guard. Got it. Okay, now let's zoom out. We might want to talk to another network. The notes mention VPC peering.
Peering is just connecting two VPCs so the instances inside can talk to each other as if they were on the same network.
But there's a big limitation here, something called transitive peering, or the lack of it.
Right. No transitive peering. This is crucial. Imagine you have VPC A and it's peered with B, and B is peered with C.
Okay, A is connected to B, B is connected to C.
Logic would suggest that A should be able to send a message to C by going through B.
Like a game of telephone.
But in AWS networking, that is explicitly forbidden. Peering is direct only. If A wants to talk to C, you have to build a direct peer between A and C.
You can't hop through the middleman.
No hopping allowed.
Okay, I see the security reason for that, but doesn't that create a mess if you have a lot of VPCs?
It creates a massive mess. The notes call this the mesh problem, because if everyone has to talk to everyone else directly, the number of connections just explodes.
The source material had a formula for this. It was something like divd n1, div2.
Oh, that's the one. It's a classic.
So if I have, say, 5 VPCs, that's 5 times 4, which is 20, divided by 2. That's 10 connections. That seems manageable.
It is, but what if you have 100 VPCs?
Oh, boy. 100 times 99 is almost 10,000 divided by 2. You're looking at nearly 5,000 connections to manage.
Exactly. It becomes a logistical nightmare almost instantly.
And on top of that, the notes say you can't have any IP address overlap, right?
Correct. If both VPCs are using that same 172.31 range we talked about, they cannot peer. The router wouldn't know which house to deliver the packet to.
Yikes. So peering is powerful but dangerous. What about a simpler connection? Say, my private server just needs to talk to an AWS service like S3.
Right. You want to keep that traffic private. You don't want your database backups traveling over the public internet if they don't have to. For this, the notes talk about endpoints and private link.
How is that different from a gateway?
Instead of opening the front door, an interface endpoint effectively drops a virtual network card right inside your private room. It gets a private IP address from your own subnet.
Wait, so S3, this massive public service, suddenly looks like it's just another server sitting in my private network.
Exactly. To your server, S3 isn't out there, it's in here. You talk to that private IP, and AWS routes it securely over their private backbone. It never touches the public internet.
That sounds much safer. And the notes mention an endpoint policy.
Yes, you can attach a set of rules to that door. You can say, this endpoint allows access to S3, but only to this one bucket and only for uploading.
So it's a filter tunnel. That's incredibly granular control.
It's vital for compliance.
Okay, moving on to speed. Edge network services. And it starts with Route 53.
Right, most people just know it as the place where you buy domain names.
Yeah, you buy a .com and you're done.
But it does so much more. The notes call it a traffic cop. It performs health checks. It can see that your server in New York is down and just stop sending traffic there.
And set it to the one in London instead.
Exactly. And alongside that, you have CloudFront, the CDN.
The Content Delivery Network. It's all about physics.
Right. The speed of light is fast, but it's not infinite. If your server is in Virginia and your user is in Tokyo, there's lag. CloudFront cheats physics by caching your data at edge locations all over the world.
So the user in Tokyo gets the data from a server down the street in Tokyo.
And gets a much faster experience. But there's a security bonus here the notes mention that's often overlooked.
AWS Shield Advanced.
Think about it. CloudFront is your first line of defense. If someone tries to flood you with a DDoS attack, CloudFront absorbs that blow at the edge. Your actual server and your VPC never even feels it.
It's like a global riot shield. Now, there's one more service here. Global Accelerator. How is that different?
While CloudFront is for content images, Video's Global Accelerator is for the connection path.
The notes say it gives you 2 global static IPs. Why is that important?
Imagine you have a gaming application. You need a steady, low-latency connection. The public internet is messy. Global Accelerator gives you a static IP as an entry point. As soon as your traffic hits that IP, it jumps off the public internet and onto Amazon's private fiber backbone.
So it's like paying for the express toll lane on the highway.
That's a perfect analogy. And because those IPs are static, it makes firewalling so much easier for corporate customers. You whitelist those 2 IPs once and you're done forever.
That is a huge quality of life improvement. Okay, final stretch. Hybrid connectivity. Bridging the cloud with what's on premises. First up is site-to-site VPN.
This is the standard. It uses encrypted IPsec tunnels over the public internet.
And this uses that VPG, the virtual private gateway we mentioned at the start.
Correct. You have the VPG on the AWS side.
Yep.
In your office, you have what's called a customer gateway, which is really just metadata about your physical router.
And once they shake hands, you have a tunnel.
You do. And the notes point out it supports automated failover with 2 tunnels, which is great for reliability.
But it still travels over the public internet. For some companies, that's not good enough.
Which brings us to the heavy artillery. Direct Connect.
This is a dedicated physical fiber connection between your data center and AWS.
It's a literal private cable. It's expensive, it takes time, but if you need guaranteed low latency and massive throughput, there is no substitute.
So to wrap this up, we've gone from a single IP in a locked room to punching holes with gateways, hiring bouncers, building bridges, and then accelerating it all globally.
When you lay it out like that, it really emphasizes that cloud networking isn't just about connectivity, it's about defining boundaries of control.
And cost. I'm still not overpaying for unused elastic IPs.
Your meter is always running.
But thinking about all this, especially that mesh formula, $1 times and 2 it raises a question for me. As these architectures get bigger, does this manual management make sense anymore?
That is the provocative thought here. We're looking at rules for manually configuring these things, but as that complexity explodes, I think we're hitting a breaking point.
Humans aren't meant to manage 5,000 peering connections.
No. I think we are going to see a move toward completely abstracting this layer away, where you don't manage the pipes anymore, you just define your intent. I want service A to talk to service B, and the cloud just figures it out.
The plumbing becomes invisible.
Exactly. The mesh becomes someone else's problem.
Wow.
But until that day comes, you'd better know your CIDR blocks.
Amen to that. Well, that wraps up our deep dive into AWS network services. Hopefully the alphabet soup tastes a little better now. Thanks for listening.
We'll see you on the next one.